Hello everyone. I am Neetu Chaudhary along with my team members Manan Sharma and Ragini Jaiswal. Today we will be presenting a topic called Mutual Information Neural Estimation, commonly known as MIND. Mutual information is a measure that tells us how much two random variables are related. It is a very important concept in machine learning because it helps us understand dependencies in data. However, the classical methods struggle a lot when the data becomes high dimensional, which is very common in modern deep learning. So the goal of mine is to build a neural network based approach that can estimate mutual information directly from samples, even when the data is large and complex. In simple words, mine gives us a scalable and trainable way to measure how strongly two variables interact using deep learning. In the next slide, we will discuss a block diagram which explains the main problem mine is trying to solve. We start with two input variables x and y. In real-world machine learning tasks, these variables often have very high dimension. For example, the image, embeddings, or long sequences. Traditional methods like kernel density estimation, k-nearest neighbors, or histogram-based estimation try to compute mutual information by estimating probability distributions. But these methods don't scale well. When dimension increase, the estimates become unreliable, unstable, or just completely wrong. This is known as the curse of dimensionality. So overall, the problem is we need a way to compute mutual information that works directly from data, does not break in high dimensions, and is compatible with modern deep learning models. And it is exactly what MIND tries to solve by using a neural network to approximate the mutual information in a stable and scalable way. Now over to Manan to explain our approached solution.
So for the approach to the mine implementation, what it does is it has basically in the inside it's a simple neural network with two input random variables x and y, which could be of higher dimensions, and the output to this neural network is t theta. T theta is actually is telling how much the mutual information of the input random variables. Now the input of this neural network is of two kinds: joint samples and marginal samples of the x and y from the from the respective joint probability distribution and marginal probability distribution. What we do is this: we feed these two inputs into the neural network, where it tries to maximize the lower bound of the dv Donsker Vardhan mutual information lower bound. And after this, the parameter updation happens, and finally we get a neural network that, given two input random variables, we get mutual information between them, how well they are correlated or not. As for our contributions, we have implemented the full algorithm as explained by me, and there are three experiments on which this algorithm is tested. The first one is the Gaussian mutual information versus rho. Second one is a non-linear dependence on three functions: x, x cube, and sin x. And third one is using mutual information as a regularizer in GAN. For the results and these experiments, I would be explaining. For the experiment one, as you can see, what we are doing is, the given the two random variables x and y, we are adding a some row amount of correlation between them. As we can see, as the value of rho increases, the true mutual information and mine both are producing similar results, which proves our network approach is working well. For the second experiment, what we did is we taking we the input pair to the network is the x and f of x plus some amount of noise. Now, as we increase the noise, the mutual information between x and y would be reduced, but our mind, for lower values of noise, that is sigma, we can get some amount of correlation between these two variables. For the third experiment, we used 25 Gaussians dataset, which has 25 clusters, as you can see in the first image. Using simple GAN, vanilla GAN for around 600 epochs, we get the second figure, which tells that it has not been clustered properly. But using regularization, a regularizer term in the loss plus GAN, we can get the cluster as shown in figure 3, which proves that our approach is working well on the different fields. Now, handing over to Ragini for the conclusion and results.
Today I will talk about the conclusion, contribution, and future direction of our work. First, the conclusion. We found that the mind can estimate mutual information very well in both linear and non-linear cases. It works effectively in deep learning situations where normal methods do not work. Also, when we use mind as a regularization in game, it's improved the quality of generated images and increased diversity. Next, the contribution of our work compared to the base paper. We reproduce the main mind result but use simpler and cleaner code. We also added the extra experiments such as the testing noise sensitivity, check multiple non-linear functions, and use mind for gain regularization. We improve stability by using EMA and tuning the hyperparameter. Finally, the future direction. First, we can integrate mind with conditional gain to improve class consistent image generation. Secondly, we can apply mind to NLP model to study how information flow in embedding and attention. Third, we can explore lower variance MI bond like NWJ to make training more stable. Thank you.